But do you know that being a good teacher, the first important thing is that you need to have a loud voice. Okay, this is not my opinion. This is from another excellent teaching award-winning teacher, professor. Okay, so he said, I forgot she or he. I forgot. Sorry, I forget. He said that the first important thing to be a good teacher is that you need to have a loud voice. Okay, I fully agree with that, because if I cannot speak loudly, and nobody in this room will understand what I'm talking about, right? So that's why I use the microphone I wear here. This is, I Google it and said any recommended microphone on internet, and the internet recommend me these things. And who use this? Candidates, mayors, or lawmaker. Do you understand what I'm talking about? 立法委员啊，市长啊，都用这个。候选人都在街上都用这个，真的，我有去看。So this is a really good, powerful microphone. And yeah, 听得懂吗？就是杰出教学奖的老师，就是其他的杰出教学老师在我们学校，他说当一个好老师，第一个要点就是声音要大，对，这样的话，我非常同意这一点，因为我小时候在上课的时候，常常都会觉得有些老师在上面讲话就讲话非常小声，而且还有一些特点的老师是这样的，他会讲话一开始讲话非常大声，然后就越来越小声。你有没有感觉这种？就是很多老师都会是有一些老师他讲话会第一个字、第二个字会大声，然后越来越小声，很奇怪。对，我们该不该跑？你看，这就是有点狼来了的那个，每一次叮，我们就说其实是不小心误触什么。那真正来的时候，到底是该跑还是不该跑 ？Anyway， 好，那我们就来开始了。Yesterday we talked about a really important concept called statically determinate and statically indeterminate. This thing is that if you have a statically determinate, which means that you can solve your unknown purely by force balance equation. However, due to the boundary condition you added by human, okay, human cause their own problem. If you added more constraint on it, which means that you have more unknown. So if you have more unknown, which means that you only have one, or typically one or two force balance or moment balance equations. So which means that you cannot solve the unknown purely by the equation of equilibriums. So you need geometrical relationship, because when you introduce a constraint, which means that an extra constraint, which means that this extra constraint also can provide you geometrical relationships. So using this, you can solve the extra unknown you introduced by yourself, right? So you can see force balance equation or equilibrium equation and compatibility equation. And don't memorize this, because this equation, compatibility equation, is based on the boundary condition you gave, okay, or problem gave. Okay, so this is the examples, and then if you want to, so typical step for 3 steps for solving this problem, this type of problem, is that list equation of equilibrium, list equation of compatibility, and list equation of constitutive law. Constitutive law means the stress relationship, okay, which is delta PL divided by EA in this chapter, okay. Okay, so if you solve this, and then you can, solve whatever you want. And also, yeah, similarly, equation of equilibrium, compatibility, and constitutive relation. Okay, and then yesterday we introduced really important concept in material science engineering, because we typically heat something, right? Heat material or cool down materials. Almost every experiment in our department related to thermal, right? Related to temperature. So this is really important. Okay, so thermal strength, which means that if you increase the temperature or decrease the temperature, the strength will change. Of course, plus typically the alpha CTE is typically greater than 0, and so it will cause epsilon T when positive epsilon T if you increase the temperature, if vice versa. Okay, and elongation just times the original length. And then important concept is that thermal stress or thermal strength. All right, so which means that thermal stress and thermal strength are not necessarily occur together. Okay, they can be one of them, or both if you have a complicated structure. For example, this is not complicated structure. So you see, if you increase the temperature, the component expand freely. Okay, so which means that it has thermal strength, but there's no thermal stress because nothing constrained it. But if you have the statically indeterminate structure, which means that the structure cannot, or material cannot expand freely, so you will introduce thermal stress. And then this is a really typical and classical problems that you increase temperature change. It doesn't say anything about positive or negative, so you don't know. Okay, so if you don't know the positive or negative, you just assume that positive. Okay, so positive because you have two walls, RA, RB, and then you need to take out of one of it and imaginarily think that there's no walls here, and what will happen? And if the temperature is a positive, you assume that, right? You will increase the temperature and elongate, and your RB also there, right, will elongate. So which means that delta T and delta B somehow together will go back to the problem, the real status. So you can see that even if you think, the RB is clearly push it back, but you cannot think emotion. Okay, you need to stick our assumption: delta T plus delta B, delta T plus delta B equal to 0, and then substitute all the stuff, and you will see the RB is negative related to delta T. So which means that if delta T increase, RB is negative because you have negative, and delta T, if it is negative, become RB is positive. Okay, so and then you know that RB is negative to RA. So now, based on the delta T, you will always know that RB and RA direction because you know their relationship. Okay, so this is quite important example. And then we stop here. We have a more complicated problem. We have the sleeve and the bolt. Okay, and it fixed by a bolt head, which means that eventually, after the temperature change, it end up has the same delta, right? Because they fixed. Okay, but because we want to know the force, so we need to imaginarily take out the constraint. Okay, so increased temperature, delta T and delta S. Delta 1, delta 1, delta 2. The delta 1 is, the definition of delta 1 and 2 is that if there's no bolt head, it expands freely. Okay, so it should be quite long, right? And then delta 2. Okay, then you can imagine that the final stage must be in between delta 1 and delta 2, right? Because delta 2 is the bolt's maximum, but delta 1 is elongate more, and which means that delta 2 will drag the delta 1 back, and also delta 1 will drag delta 2 to the right hand side. So you can imagine that makes sense, right? So your final position, it must be in between. Okay, this is the final delta. So actually this one is what we are going to determine. So when I say delta 1 will make the delta 2 further, what is the cause? Of course, this thing will be dragged by a so you can imagine that it must be it must be something drag the delta 2 to the right hand side, and it must drag the sleeve to the left hand side. Okay, so this is a force done by the bolt head, right? Bolt head. So, and well, maybe you will ask, why not we assume that this one is going to the right? We could, but you kind of for sure that these two forces is going to compress that, right? So you are pretty sure. So there's no need to assume that in a positive way. But if you want to do that, feel free. Yeah, you can do that. But and if you stick your assumption, you eventually will get exact and accurate answer. Okay, so you can imagine that the PB, this is PB, okay? The force in the bolt material going to the right hand side, and the force PS, sleeve, okay? These two, or maybe it's a sleeve, so it should be a circle, a tube, right? So the delta 1 will be pushed back to the final stage by PS. And then, so this is delta 3. So delta 3 is pushed by PS. And okay, I should make it longer. Okay, and the delta 2 end should be pushed to delta 4 with a delta 4. Okay, delta 2 add delta 4 due to the PB. So now you can kind of understand the mechanism. Firstly, delta 1 and delta 2, and then delta 1 pushed back by the PS and with the delta 3, and delta 2 pushed by PB to the delta 4, okay? In additional, delta 4 is introduced. So, equation of compatibility. Okay, delta, the final delta is delta 1 minus delta 2. Or you can say delta 3. Sorry. Okay. 1, 3. I will adjust delta 2, delta 4. Okay? Delta 1 minus delta 3 and delta 2 minus plus delta 4 will be equal to delta. And alpha s delta t times L will be delta 1, right? Expand freely. And delta 3 is PS, pushing it back with the delta 3, right? The distance. So PSL, PL divided by EA, right? Divided by ES, AS, okay? And then alpha B delta TL plus PBL divided by EBAB. Okay, so you have a equation of compatibility. I will say it is equation 1. And then I have equation of equilibrium. Okay, equilibrium. The force is quite simple here, PS and PB. so PS equal to PB. Or you can say PB minus PS equal to 0. Okay, and this is equation 2. So yeah, that's it. Oh, by the way, you can notice that the value here, here is the value, and this minus is indicating its direction, minus and positive. Okay, so you need to be careful about this. The delta 3 should be in the negative way to put it back, push this back to here, and the delta 2 is going to push delta 4 to the right hand side to this final stage. So minus and positive is quite important here. Okay, then next stage. So based on equation 1 and 2, okay? Well, PS equal to PB, right? So, alpha S minus alpha B times delta T ESAS EBAB and ESAS plus EBAB. Okay? So we have this relationship. It's too far away. Alright. Then we are ready for sigma S and sigma B. Sigma S equal to PS divided by AS. And sigma B equal to PBAB. Okay? So, may I copy and paste alpha S delta T AS. And that's it. Very good. I love digital blackboard. Okay, and you know what is the value of it? Okay, very simple. And delta, what is delta? Delta equal to, what is delta? You can have this, right? Delta equal to alpha b delta TL and plus. Yes, I just copy this, right? And then how to do that? We just substitute PB here, and then you can get your value. Okay? Very Okay? So this is just a concept. Okay? Concept. Cool. I believe you understand the rest of the part. Okay? It's just the substitution. But the most important thing is that I kind of demonstrate how to dealing with this kind of complicated system that you need to imaginarily take out the constraint and then let it expand freely, and then we need to put it back. So you need to have a force on it. Okay, that's the thing, that really important concept for thermal effect. All right, that's it. So while you are writing the note, taking the note, I can share with you. I just found that or discovered that Taiwanese typically will, when we do something wrong, we will say sorry with a really high frequency and many times, right? Just like I did, right? I said sorry, sorry, and 或者是对不起。对，我发现这件事情，我不知道为什么，你们会这样吗？你们会忽然对不起，还是说你觉得对不起一次？不知道是我这一代还是怎样，因为我从小国中的时候打篮球嘛，然后就例如说打手或者是撞倒别人，就会说对不起，然后就是很紧张的感觉。那当然。出了国以后，听到他们就是sorry， 然后我就会觉得甚至有几次我就跟他们说 sorry， 然后他们就说你为什么要讲那么多次？所以他们就觉得我很怪。那我觉得啦，可能我从小的教育或者台湾人的教育就是觉得说，我们一定要有礼貌，然后不要对不起别人。那如果你今天做了一个错事，你就会很想要挽回它，所以你就对不起 ，sorry， 这是我以前从小就是这样，但我不知道你们这一代会不会这样，会吗？有听过别同学会说很快的 sorry 很多次，或者对不起很多次吗？好像没有，那就是代沟了因为我的同学都是这样。好，真的你们不会这样的？不会啊！哎呀，糟糕啦，这就是代沟，所以以后讲这么就是显示你自己很老的意思。哎呀，原来这种也会显示年纪啊，真糟糕。而且我甚至以为这是通病，因为我身边人都是这样，这是同温层。对，我还真的有跟我同学讨论过。就是说，而且他现在是美国的教授，这样，所以我就跟他在美国聊天的时候，我们就真的都会，你看到他用英文去跟外国人讲 sorry， 然后我就说，你有没有发现这件事？然后他说，对，有发现，对，好吧，原来是这样。最近我看到一个那个 脱口秀，虽然我忘记他，我不知道他叫什么名字，但是有一个稍微脸圆圆的一个男生，然后头发卷卷的男生，然后他不是 English native speaker， 然后讲 English 的 stand-up comedies， 然后他就有说一些蛮好，就是网络推播，我就觉得蛮好笑的这样。然后我觉得他里面最有名的一个桥段就是，他说他英文很差，然后一直在学习新的英文的单字，然后他最近学到了一个英文单字很长，然后很特别，然后是这个意思，这个单字的意思是你倒太多咖啡给我了。他就说是什么呢？他就说，有听过吗？没听过，超高。他讲比较好笑啦，但是你没听过外国人说，这样吗？没听过吗？没有。好，我真的有看过，我真的在外国，在喝咖啡的时候，或者是喝倒茶，就是不要了，停下来，这种感觉，他们真的会这样子哦。所以我觉得这个跟我们的对不起，sorry，有一点点像。那他讲这个东西的时候，全场的大笑，那是因为他们真的会这样子。好，所以你们不笑，可能是因为你平常不会这样。你会说，好了，这样这种感觉啦。好，这样好。那接下来他就开始讲其他的事情。总之，这一段我觉得蛮好笑的。那好，我可以推荐给大家哈。那就这样，可以看可能分享到我们的 Facebook Club 里面。对，很好笑。好，就这样，不管。下一个。Okay, next one. I should translate. Anyway, I just recommend that you can watch stand-up comedy quite often because it will make you happy. Okay, make you laugh. Right. Stress element. Stress element is so important. Remember, I talked about the indirect shear. Indirect shear. Okay? Indirect shear will make your element with a pure shear, right? And also we introduce axial loaded member with axial loaded force also cause shear stress. And then at that time I said I will introduce it later. Here is the time, okay? Stress element. So stress element is a tiny element. You can imagine that this is a point, okay, in a material, and every material has the material point, and then you can think one of it is a cube, okay, it's a cube, and it's called stress element, and you can analyze the stress status at that point by using stress element. Why using element? Because they have phase. When you have phase, which means that you have orientation. Okay? So each orientation represents a component in that direction. So you can say, okay, this material point has sigma x in that direction, sigma x or sigma y or sigma y. So you can see that the element actually tell you the orientation because you have surface, right? Surface has normal vector, okay? So that's it. And then remember that we have bar, okay? Has a P acting on the surface, and I want to cut it to see the stress in that cross section. So we cut MN section, and because the MN section is far away from the loading point, so we expected that this surface has uniform stress, okay, uniform stress in this. So you can see sigma x equal to P divided by A, no problem. And then if we just see one point of it, 1 point, and then we just plot a stress element. We say why we have a C here? Anyway, so this is a point, and then you can say, okay, this stress element has sigma x to the right and sigma x to the left. Okay, and maybe you will ask, you only plot this, right? Yes, we only cut this. But if you want to cut the rest of it, you want to see this thing, you need to cut. Okay, so cut, and then cut, and then you has the stress in this direction. Okay, so this is a stress element. Okay, imaginary. The size of stress element is assumed infinitesimally small, which means that infinity, it's really small, just like a point. Okay. Now the really important and really difficult part is coming. Stress on inclined section. Let's take a look. So the P is still here. Okay. Now we are seeing through the XY plane. Okay, to the side view. Now, because the loading condition is unchanged, right? So you can imagine that the stress element you just draw still has sigma x, right? But now we are asking you, how about if I don't want to draw the stress element vertical and horizontally? I want to draw it with the angle. Can I do that? Of course we can do that. Okay, so now I want to draw the stress element like this. Why not, right? And the element surface, the main surface here, is tilted with theta angle. Okay, so you can imagine that this direction and that direction is x1 and y1. X and y are original coordinates, but now you have x1 and y1 local coordinates, and this x1 y1 is, for the main surface, 主角的面, okay? So let's take a look. I want to see this stress element, the stress status. So I just cut it. I cut it and leave the left hand side, okay, and neglect the right hand side. So cut it, you see that PQ, right? And then you can imagine that these force should be like this, right? And we want to know that this force can be decomposed into two components. The first one is along X. The other is parallel to the X, or we can say Y1. Sorry, parallel. This one can be along X1 direction, and this one can be along Y1 direction. And this is the resultant force, okay? Resultant stress, okay? So this is a component. These two are component of this one. I hope you can understand what I'm talking about. So you see P. The P causes this, but the P can also decompose into n to the x1, v to the y1. So n will cause this, v will cause this. Okay? So I will name it sigma theta because it is following the theta angle. And also I will call this tau A. This is shear stress, right? When I talk about the shear stress, the definition is that the stress is acting on the surface and parallel to the surface. See, this is the surface and it parallel to the surface. So this is tau theta, because it's on the theta plane. Okay, sigma theta and tau theta. So yeah, that's it. So now, actually I have done the explanation, so you can now understand what does that mean, right? N is the normal force on the PQ plane. Okay, what is that? P times cosine theta. All right, and V is P times sine theta. N and V. Okay, so you can see N and V are the components of P. 分量啊，分量。Okay, and sigma theta and tau theta equal to N divided by N divided by A1, V divided by A1. Okay, what is A1? A1 is the surface of the area, right? This surface area, PQ area. We know that PQ area is always greater than the real area because it has the oblique, okay, oblique angle. So let's take a look. This one is what we're going to talk about. A is the original cross-section area, and the purple one is the PQ with the angled area. So you can imagine that, where is the theta? Oh, this is the theta, right? So this is the theta because you oblique has the oblique theta here. Okay, so this is theta, and you can imagine that this line is longer than the original height. So you can see that B and H, width and height. So this one is height divided by cosine theta. Height divided by cosine theta times BH times B. So you have BH divided by cosine theta is A1. So you can see that, A1 equal to A divided by cosine theta. So you can imagine that A1 is greater than A because cosine theta is always less than 1. You divide this number, you will make A1 greater than A. So now you get it. So A1 substitute here and here. So sigma theta N divided by A1, tau theta V divided by A1. And notice that we have a minus sign. Okay, we have minus sign. Why? Because your N here is in the positive x1 direction, but and your theta, sigma theta, suppose your N is assumed to positive x1, and the sigma theta also along positive x1, but your positive N make negative tau theta along minus y1 direction. So you need to have a minus sign here to indicating that this tau theta will always in different opposite sign with the sigma theta. Okay, with n. Okay, excuse me. Right. So if you can understand this, you can have sigma theta equal to P divided by A cosine square theta. Tau theta is minus P divided by A sine theta cosine theta. That's it. Okay, that's it. So you combine these two. Okay? Nice. So, if we set sigma x equal to P divided by A, of course, you know sigma x equal to P divided by A. See? Okay? So, cosine 2 theta equal to this one, sine theta cosine theta equal to this one. You know that this is the senior high school sine cosine equation, right? Formula. So you set this, you will end up sigma theta equal to sigma x cosine square theta. Tau theta is minus sigma x sine theta cosine theta. Alright? So you can imagine that this is equation, formula. You can kind of memorize it. So whenever you have a force on it in the actual loaded member, every angle, inclined section, you can use this because theta is a symbol, so you can substitute any value of it. So now you are ready to obtain all the section, different angles, and to determine the component of stress, sigma theta, tau theta. Okay, and then you notice that even you loaded that in the actual way, you still have the shear in different angles. Okay, so very important. I will give you a star here. Okay, please memorize it. Okay, I'm sorry. You can not memorizing it. It's okay, but you will use that quite often. Okay. Then I will give you maxima, normal, and shear stress. You know that this is sine theta cosine theta, right? So which means that it has maxima and minima due to the theta change. So when cosine 2 theta is maxima, which means that theta equal to 0, theta equal to 180, sigma theta equal to sigma x, which means that, yeah, of course, your theta equal to 0. Okay? So 0 degree. So your surface is sigma x, of course. Right? And then this is theta 180 degree. When you rotate your main surface to the 180 degree, again you have sigma x. So you see, sigma theta equal to sigma x when theta equal to 0 or 180 degree. And you notice that when you substitute theta 0 and theta 180 degree into the tau formulation, you have 0 shear stress. No shear stress. No. You see, there's no shear stress. Okay? And another thing is that if you substitute 90 degree or 270 degree into this, you will get 0 sigma x1. Okay? So no sigma y, or you can say no sigma x1, because when you substitute 90 degree, which means that you have to rotate your stress element main surface on the top. So this 90 degree, sigma x1 is upward along original y. And so you substitute 90 degree and you got 0. So no actual stress here, no more stress here. Then, when sine 2 theta is maximum, whoa, it becomes 45 degree. If you have 45 degree, you have tau theta equal to half sigma x. So you have half sigma x. And this is theta 45 degree. And if you substitute 45 to this one, you have a little bit half theta sigma x. So it's not 0, okay? So interestingly, they are not kind of fair, okay? So in the maxima 0 and 180 degree, you only have normal stress. But if you have a maximum shear stress, you still have some normal stress, all right? And remember that shear stress occurred in pair, right? So its opposite side must has this. And again, here, and here, and here. And also has half sigma x. Again, the area is theta equal to 45 degree. And this is 135 degree. And this, you add it by yourself. Adding 90 degree, and this adding another 90 degree. All right? So maybe you are kind of still need to, process a little bit. So I will encourage you review this. This is difficult. I hope you can understand what I'm talking about and review this during this week. Okay, during the weekend maybe. Okay? I guess, this is all for today. And thank you. And if you have any questions, just come here. Thank you. Bye. 有问题来问我，这边有一点点复杂。